Slowly people will join, I think. I started the recording, so
Wait for 5 minutes. People are joining.
Emma,
People
we'll
are
wait.
joining. We'll wait for 5 minutes.
Yeah, wait. We are having very less time because it is 27 now. So maximum we may get around 15 to 16 periods, even much lesser than that. I have to complete 2 units, right? Because 24th is the last. That's what they are telling. I'm not sure. Not official communication came. In between some your exams, some periods will be not there. So we try to cover fast so that one big important big unit is there, fifth unit. So people slowly are joining, I think. Let us go to this fellows, right? So in last class we are discussing about this. The equilibrium conversion will decrease for exothermic reactions and increase for endothermic reactions with temperature. So if K is greater than 1, that means it is almost an irreversible reaction. There is no reverse reactions. You can see it's almost XAE is almost 1. Right? But if the K is less than 1, very much less than 1, then very low conversion is possible, because you can see here the conversion is around, equilibrium conversion is around points. Right? So this is the important thing which you need to remember. With the temperature, the equilibrium conversion will decrease for exothermic, and endothermic you get increase. Right? So with that, there are three graphical procedures. You can see here, there are three variables here: concentration, temperature, and rate. So out of the three combinations, you can put a C, because there are three variables here. Two variables you can put on a graph, but the third variable you have to keep that as a constant. So how we do is we draw C versus T with the same R1 or R2 or R3. So as we go this side, that means your concentration is increasing, or temperature, your R also is increasing. We can put the other way around. You can put R on the y-axis, T on the x-axis, and you can write with the same C1, the recomposition C1. For a different temperatures and rate, you get the same C1, this curve, like that C2, C3, like that. Or you can put R versus composition with the different temperatures. So out of these three, generally we go with this. This is more convenient to calculate the reactor size. That is C versus T, and then you write the rates. C in the sense you can put either C or XA, because C is concentration is CA is CA naught into 1 minus XA. From that XA you can calculate. Am I right? So C versus T with the R, in the sense C instead of C we can put XA also. Understand? So for the different XAs, T, and you can draw the curves. That is what we will do in the next thing, to calculate the reactor size. Yeah, please listen carefully. Somehow I try to teach now today itself, but we'll see how far it goes. Otherwise, we'll take again. Right? So important thing here is there are 4 kinds of reactions. The 4 kinds of reaction can be exothermic or endothermic, irreversible, reversible. So there are four combinations here. The reactions can be reversible or irreversible, exothermic or endothermic. You know what is all that means. Irreversible process is nothing but A is giving R. Reversible is A is giving R is giving E. Exothermic process is you are giving the heat or heat is being liberated inside. So heat is liberating. Endothermic in the sense you need to give the heat for the reaction to happen. Exothermic, the reaction when it is proceeded, it will give out the heat. Understand? So there are four combinations. One is reversible exothermic, irreversible exothermic, reversible endothermic, irreversible endothermic. Right? So that four combinations, right? Out of the four combinations, we see three or anything, right? So either it is irreversible exothermic or endothermic, reversible endothermic, reversible endothermic, and irreversible exothermic. So in the first thing, both is shown irreversible process. That means A is giving R. Both exothermic and endothermic this curve. Whereas if the process is reversible, then you get exothermic different graph, endothermic different graph. Yeah. Now, what does this means? Now you are calculating C versus T. We told that for drawing, for going for a reactor size, we out of the three combinations, we take this combination C versus T. So if you know concentration time data, then R you are plotting. The concentration you know, or if you know the concentration, you can calculate even the X's, that is conversion. That is what I am trying to do. XA versus T I am drawing with the definite RAs. For all the things it is same. This C versus T is nothing but XA versus T. Because C you can convert to XA. C is C naught into 1 minus XA. You know the initial concentration, then 1 minus XA, you can put XA is 1 minus C by C naught, right? So based on that, you can calculate the XA, right? This is 1. 1 is nothing but the maximum conversion which you can get. And 0 is the minimum conversion. I'm writing in terms of 1, 0 and 1, right? That is because it is dimensionless. It's not 100%. You can assume it is 100% also. So 0 to 1, XA lies between 0 to 1 in all the process. Now what is happening in irreversible exothermic or endothermic process? So irreversible exothermic or endothermic, the reaction is not reverse. So it is a single reaction where A is giving products. So it can be exothermic or it can be endothermic. Endothermic in the sense you are giving the heat for the reaction to happen. Exothermic in the sense the reaction is liberating the heat out. So you need to go for some cooling. So in both the process, if you see, as you increase the temperature, the rates will increase. Because minus RA is K into CA. K is a function of temperature. So as the temperature increases, your K will change, which changes your minus RA. At lower temperature, the RA, R is nothing but RA, right? R is general form, RA is only a specific to A gives product. The rate is 1, the rate is 10, the rate is 100. If you look at this particular thing, as you increase the temperature, you can see at this particular temperature or whatever temperature you want, the rate is going on increasing. The rate is going on increasing. So the rate will go to maximum conversion is 1, almost it touches. Both for exothermic and endothermic. because this is the irreversible process. There is no again back reaction is there. So irreversible process, even it is exothermic or endothermic, it is always better to keep your temperature at its highest. High temperature will give you high rate. High rate will give you more conversion. Correct? From this graph. Now, we'll come to one more point. Irreversible, when we come to reversible process, reversible endothermic. So reversible endothermic in the sense, what does that mean now? The process is reversible or the reaction is reversible. That is, A is giving R is again back giving A. But it is endothermic. Endothermic in the sense the reaction is happening only in the presence of you need to give the heat. You need to give the heat, right? When you need to give the heat, it always forms like this. Even it is a reversible process, it forms like a irreversible process for especially for endothermic. The high temperature will give you high rate. High temperature will give you high rate. When R is 0, when the what do you call the temperature is 0, when R is 0, that is the rate is 0. This is forming like this curve. That's a H-shaped curve. Afterwards, when the temperature is increasing, it forms like this. This is for a reversible endothermic process. So here also you can tell that as the temperature is increasing, your rate will increase, so that's your conversion. But the maximum conversion is almost 1. Now what will happen if it is reversible exothermic? That means the process is reversible. A is giving R is giving A. The reaction is exothermic. So the heat is being liberated on its own. When the heat is being liberated on its own, what will happen? The conversion is, as you increase the temperature, you see any curve, any R is 1, R is 10, R is 10, 100. As R increases, to a certain extent it will increase and then drops. Because the reaction, it is increasing in its temperature, reversible exothermic, you need to cool the temperature so that your curve it comes like this. Your reversible exothermic, you can see here, as you increase the temperature, the exothermic reaction, your XAE comes down or equilibrium conversion. That is the same thing happening here. If there is R is 0, your curve will go down. That is what we saw here. As you increase the temperature, your exothermic XAE will come down. This is a reversible process. So you are talking about XA in the sense this is XA equilibrium. So it comes down. Then when R is 1, again it it starts with somewhere and then goes to a maximum and then come down. Even R10, it goes to a maximum and then come down. Even 10, it goes to a maximum 10. Afterwards, still it is more, it goes, and then it joins here. At a higher temperature, your XAE is very less for any type of rate. So from this thing, we can understand that for a irreversible exothermic or endothermic, your highest temperature, if you want to get a high rate or high conversion, it is always better to keep your temperature at its maximum. So high temperature will give you high rate and high conversion. Not only for irreversible exothermic and endothermic, even for reversible endothermic, high temperature is always preferred. But it is not always the case for the reversible exothermic. If you are having a very high temperature, you see the rate, the conversion is very less. So for a reversible exothermic process, you should not keep at a very high rate. You have to see to that there is a high point, there is a what do you call? There is a high point here. There is a maximum here. there is a maximum here, and you have to operate your system which is having a very high temperature. So in this process, if you go along this, your temperature goes on decreasing. You see here the temperature is high. If you go up as the locus of the point, here the temperature is less, here the temperature is less, here the temperature is less. So you should go on decreasing the temperature in such a way that you get the maximum rate, the maximum conversion. That is why in exothermic processes, we will decrease the temperature by inserting some cooling coils or taking out the products out that again you are sending in, right? So based on this three, that is, this is for both exo and endo. This is for reversible endo. This is for reversible exo. This point is very important because these almost similar. At a high temperature, it favors your reaction. Here also high temperature favors your reaction, but not here in exothermic process. High temperature will favors only less conversion. Therefore, you need to decrease the temperature in such a way that you need to get more equilibrium conversion, especially for reversible exothermic. Any doubt here?
No, sir.
No, sir.
Discard this. Again, I'll come back. Now we'll have some notes regarding this. There is no notes. I think notes is here. Yeah, we'll discuss this, then go back to this. Okay. Now, what is this optimum temperature progression? Optimum temperature progression, this is a very important 2 marks question. What is this optimum temperature progression? OTP. It is the defined as the temperature progression which minimizes the size for a given conversion of the reactant. Okay, he's asking about a given size, right? So, okay, let me talk this and then go. It is defined as that temperature progression which minimizes the size. When you minimize the size, when the conversion is more, when the conversion will be more, when the temperature is more, the conversion will be more. So you can do more conversion at a very less size. So for a given size or minimizing the size for a given conversion, you want some particular conversion. What should be the temperature? That is what we call as optimum temperature progression. Now for irreversible exothermic or endothermic, you know that these are the curves. This is R is equal to 1. Like that it goes on increasing. So in all these processes, we know that the maximum allowable temperature, whatever is maximum allowable, there you get more rate. Therefore, your conversion is also will be higher. If you operate your temperature at this maximum temperature, your size of the reactor also will be less. This is for irreversible, exothermic or endothermic. Now we'll come to reversible endothermic. Even in reversible endothermic, it is like this. If when R is 0, it starts somewhere. This is again XA, right? XA, E also you want to put because reversible. So as R increases, again your reaction starts a bit up in this particular thing. Here also, the maximum allowable temperature is you get a maximum rate and you get more XAE. Again, what is this maximum temperature allowable? Can anyone tell what is that maximum allowable temperature? It can be infinite temperature. So the more temperature you give, more will be the rate. That does not mean that I go on increasing the temperature. Because if I, just like a balloon, right? Balloon, there is a limit to the balloon. If you go on blowing your air, the balloon becomes big, 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 big. After there reaches a point where it will burst because it cannot hold more than that. The same here, reactor. The reactor that is concentrate. The material of construction, that is what we call MOC. the material of the construction of the reactor plays a very important role in what temperature you are going to fix. If the material can withstand 500 degrees centigrade, then it is better to go about that particular thing. If the material is withstanding only 250 degrees centigrade, and if you are trying to run the reactor at 300 degrees centigrade, then it's no point. It will blast. That is why we call it as maximum allowable. Who will give you this limit? This limit will be given by the material of construction of the reactor, both for irreversible exothermic, irreversible endothermic, or reversible endothermic. Now we'll see reversible exothermic. Reversible exothermic, we already talked about, there is a high curve, there is high point, and then as you increase, the rate will change in this particular direction. But the locus is shifting. The locus in the sense, the maximum point locus is being shifted. So what you do is, you try to be at this particular maximum limit. What is allowable? Again, it depends on your material of construction. Once you go there, then you try to decrease the temperature in such a way that you will be on this locus of the maximum rates. This is the locus of the maximum rates. That is what we call locus of maximum rates. That is called as the best path. So you go on decreasing the temperature so that at this particular temperature, you will have the maximum rate. At this point also, you have the maximum rate for that. At this point also, you have the maximum rate. So you are always at the maximum. Therefore, when you are at the maximum, there will be some more lines here, which I didn't draw. So don't think that in between there won't be any lines. There will be multiple lines. So this is the locus of all the what do you call maximum rates. So if I go in this particular path, then I will have maximum rate. Therefore, I'll get maximum conversion. The point at which this temperature progression, which minimizes the size because you want more conversion for a particular size. If you are at that particular temperature, you know that your rate is also high. Therefore, the reactor size will be much lesser. The point or the temperature at which your reactor size is minimized for a given conversion, whatever may be your conversion, that you call as optimum temperature progression. It's a very important 2 marks question, even essay question also. You need to draw this and then explain this. So we'll see some points based on this. Any doubt here? This is the same thing as the previous one which I discussed. But here I'm just putting one temperature where it is maximum. So hope no problem. Now I'll go for some notes. Now you see, for an irreversible reaction, both exothermic and endothermic. So I'm talking about this particular curve. I'm talking about this particular curve. So what is the first point? The rate always increases with the temperature. Yeah, right? That is what we saw here. The rate is always, this is rate less, this is rate more. The rate is always increases with the temperature. For any composition, right? For any composition, because for any composition in the sense XA here. So the highest rate occurs at highest allowable temperature. That is what we just discussed here. This is the maximum allowable temperature. This temperature, what is the temperature, maximum allowable temperature, is set by the material of construction. Material of construction or by the possible increasing importance of the side reaction. There will be one more case where the more, if you increase the temperature, more side reactions will happen. If there is a series reaction or a parallel reaction, even though it is irreversible, at more temperature, what happens is side reactions will increase. So that temperature will be limited by that particular side reactions or by the materials of construction, right? So we'll see the second curve. This is the curve which I am discussing now. This is reversible endothermic process. So you are giving the heat, right? So reversible endothermic, this is irreversible exothermic or endothermic. Either you are giving the heat or the heat is being liberated. Whereas if it is a reversible endothermic, that means you are giving the heat So for that process also, for endothermic reactions, a rise in temperature increases both the equilibrium conversion and the rate. That is what we saw here. A rise in temperature, both the XAE, that is equilibrium conversion, as along with this rate is going to increase. Thus, as with the irreversible reaction, the highest allowable temperature should be used to give you the minimum size required for a particular conversion. So this and this is both the same. Again, how the temperature will be fixed, either by materials of construction or by the side reactions. The more side reactions are coming, then you will fix to that. You want to eliminate the side reactions. So you fix a temperature. At that particular temperature, you try to operate the reaction. Now I'll talk about this. This fellow. This fellow is reversible exothermic. So we know that there is a locus of the roots, high temperatures. So we need to decrease the temperature in order to have high conversion. That is what here. For a reversible exothermic, the forward rate reaction speeds up, but the maximum attainable conversion decreases. That is why it is here. Forward reaction is shooting up, but again reverse reaction also starts. Therefore, your XAE, equilibrium conversion, will decrease. Thus, in general, a reversible exothermic process starts with a high temperature, which decreases as the conversion rises. Now you see, you start with a high temperature till this particular point, then starts decreasing, so that your conversion, you can see here, the conversion is at this particular point is here. At this, if you go on in this particular way, the conversion will go on decreasing. So you have to go in this path. Therefore, simultaneous your conversion will go on increasing. Am I right? That is why for a reversible exothermic process, definitely the temperature should be, or temperatures or pressure should be reduced, so that you need to increase your conversion. Right? So this we discussed now. Any doubt here? So we need to calculate how this minimization of the size is being done. That I will show now. Yeah. Any I'll just delete all this. That I will come back again. Yeah. Any doubt here? Yeah. Again, we'll repeat. For irreversible reactions, the rate always increases with the temperature at any composition. So the highest rate occurs at highest allowable temperature. This temperature set by the materials of construction or by the possible increasing importance of the side reactions. For a reversible endothermic process, for endothermic reactions, a rise in temperature increases both the equilibrium conversion and the rate of the reaction. Thus, as with the irreversible reactions, the highest allowable temperature should be used. For irreversible exothermic processes, the rate of forward reaction speeds up, but the maximum attainable conversion decreases. Thus, in general, a reversible exothermic reaction starts at a high temperature, which decreases as the conversion rises. That is what this. This is what we call as optimum temperature progression. Now we'll come to how we can minimize this size. How can we find out this particular size? Now we'll go back to this. This already I discussed, right? This irreversible processes. Now let us take some particular XA versus T. Now I am just talking about how to calculate the size for a different reactors. Either it is plug flow reactor or a PFR or a combination or whatever it is, right? So for that, I'll just see, read out the procedure, see whether you are able to understand or not. The size of a reactor required for a given duty in the sense, either it is conversion or whatever it is, concentration or whatever it is. For a given temperature, progression is as follows. So for a given temperature, the size of the reactor for a given duty, either for particular concentration or particular conversion. There are 4 points here. Draw a reaction path on XA versus T plot. So we already discussed that we are always going with the XA versus T plot. This is the operating line for the operation. Draw the reaction path. The reaction path is nothing but this. For a XA versus T plot, this is the operating line for the operation. Find the rates at which the various XAs along this path. Plot minus 1 by RA versus XA curve for this path. Find the area and the curve. This will give you V by F naught. Then we can calculate the volume. Yeah, I know you didn't understand anything now. Now let us go point by point. Yeah, please listen carefully. Here you get a lot of doubts. Some doubts, again, it is very difficult for to clarify also. I should openly accept that. You get a lot of doubts here, right? So now I'll show. XA versus T. We know that XA versus T you are drawing. So for this curve, let us assume that you have no RAs. RA at 0.01, RA at 0.02, RA at 0.05. So you know 3 rates. You know the 3 rates with the 3 different temperatures and different XAs. Now try to plot with a different temperature, different XAs and same RA. So you get a curve like this. If XA, different XA and different T's, you get this particular curve that is which is having the same minus RA, that is 0.01. Like that, different XAs, different T's, you draw one line with that is you have to plot first and then draw a smooth curve. That is for 0.02. Again 0.05. Okay. These 3 you done. This from the in the problem if he gives it is okay. Otherwise you have to calculate the rates. How to calculate the rates? I think there is one problem in Gavane which you need to know to draw how we draw this particular thing. That we'll see a bit later, right? Now what we have to do, this is the first point which we did. Draw the reaction path on XA versus T curve. We had this plot now, different XAs, different T's. We draw the reaction path, correct? We draw the reaction path. What is the reaction path now? Let us assume that at a particular temperature, you know that the reaction path is like this. It can go like this, it can go straight, wherever it is. If it is an exothermic process, the reaction path is this. This is the rate at which the reaction is maximum. So you have to go in this path. So for this particular thing, let us assume the reaction path is very arbitrary. It can go any shape. So let us assume that the reaction path is like this. It is going like this, it is coming like this, and it is going like this. Okay. This is the maximum good path for that, right? So that is what this. Draw the reaction path on XA versus T plot. This is the operating line. Find the rate at which various XAs along the line. So what we need to do now, when you draw this reaction path, it is cutting the different rates. This is one rate, this is one more rate, this is one more rate. How many rates it is cutting? So this is one rate which is being cut. Here there is one more rate which is being cut. Here there is one more rate which is being cut. Here there is one more rate which is being cut. Here there is one more rate which is being cut. Am I right? How many rates it came? 1, 2, 3, 4, 5. There are 5 rates through which this reaction path is cutting. Okay, this and this reaction path is same, but still there are 5 rates which is being cut by this reaction path. Correct. That is what I mean by this second point. Find the rates at various XAs along this path. So this particular thing, you know what is XA. This is particular thing, you know what is XA. At this particular point, you know what is XA. At this particular point, you know what is XA. At this particular point, you know what is XA. Correct. So for different XAs, you are drawing this particular path. For this particular thing, what is the rate here? This is the rate is 0.05. Here the rate is 0.02. Here the rate is 0.01. Again here the rate is 0.02. Here the rate is 0.01. Correct. So different XAs, different rates is coming. Now you draw minus 1 by RA because you calculated what is this cutting point, different RAs. You do 1 by RA, minus 1 by RA. Then this particular thing, 1 by 0.01 is 100. 2 by 0.01, some value you get, right? 3 by 5 by 0.01 by 100, right? Divide 1 by this particular thing, 20, 50 and 100, let it be. Now what you do is, you try to draw the same thing, XA. This is XA. This is XA. Now you draw this particular XAs, right? So 1 by RA and XA, you draw a plot. So for this particular thing, what is this point? This point may be 0.1, right? Let it be 0.1. For this particular 0.1, what is the rate? The rate is nothing but 0.05. 1 by RA is 1 by 0.05 is 20. That is what you are plotting here. For this particular 0.1, you draw that particular thing. Like that, here it is 0.2. How much it is? 0.02. So 0.2 somewhere here and 0.02, 1 by 0.02 is maybe around 20 or something. So it will be somewhere here. That is what? 50. Like that, for different thing, you try to plot. This is the plot for that particular thing. Now you want a conversion of around 0.8. So this will be the conversion of 0.8, this maximum line. So the area under this particular curve will give you the area of required or the volume required for the plug flow reactor. This is V by FA0. That is what I think. Plot minus 1 by RA versus XA curve for this path. Find the area under this curve. This will give you V by FA0. That is what. V by FA0 for any particular what do you call conversion, you can find out V by FA0 from this particular area under the curve. FA0, you know, you can calculate how much is the volume required for this conversion in a non-isothermal process. This is for plug flow reactor. This is for plug flow reactor. We know that plug flow reactor, the area under the curve. Now, for suppose, if this same 0.8 conversion, I want a 0.8 or 0.7 conversion in a mixed flow. If it is a mixed flow, then what I have to do? I know what is the conversion, 0.7. This is the 0.7 curve somewhere, right? So I know where is the temperature it is being started. I know the temperature at which it is being started. So that particular thing, I calculate all the rates. I know what is the rate, 0.01, 0.2, 0.3. So with this particular thing, a straight line, again, how much will be the slope of this? I'll tell you later. This depends on T is T0 into beta into XA. That I'll show you a bit later. How much should be the slope? I can draw like this curve. I can draw like this curve. I can draw like this curve also. But how much should be the slope? Wait for some more time because I need to calculate the adiabatic temperatures. Then I'll tell you. So till now we assume that there is a slope which is positive. So with that slope, you try to project it up and see to that at 0.7 where it is cutting this particular thing. that will be the rate, right? That will be the rate. So that rate you put minus 1 by RA. That rate is 0.001. It is thing 1 by 0.001 is 100. So that this is the rate curve, and 0.7 you want. So we know that the area of a rectangle is what is the volume of mixer reactor. Therefore, this particular thing will give you V by F naught. From this, we can calculate V. So area under the curve will give you plug flow. You give area of a rectangle, it will give you mixer flow. Now, for suppose, if it is a recycle reactor, what should be done? Let us assume recycle ratio as 1. So one part out of the 100 parts is being recycled. So it's almost like a plug flow reactor. Am I right? It's almost like a plug flow reactor because recycle ratio is very small. So again, you draw again the same thing because with the same slope, some slope. Again, how to calculate this slope, I'll tell a bit later. With some slope, depends on the slope. You try to cut the curve with this particular thing, again 0.7 or 0.8. Here he is assuming it is 0.8. So it cuts the curves at a different point. This curve, it is cutting at 2 points, right? So the 2 points is this and this particular thing, right? So what thing it is going to cut? This here it is cutting, here it is cutting, here it is cutting, here it is cutting. So for that, you know what is the conversions. This is the conversion and this is also the conversion. So put 1 by XA, 1 by RA because this is minus 0.1, 0.05, 0.5. This is the XAs. You draw XA here and minus RA. So and if you draw the curve, it comes like this. Now you see 0.4 and 0.8. This is the maximum conversion you want. And this is the conversion where it is being done. So along this path, you know that this is the entire thing is the area of required for the recycle reactor. Out of this, we calculate this particular thing because it is more like a plug flow. Therefore, the area under the curve is nothing but the area or the volume required for the recycle reactor, right? So this how we calculate the size required for this particular either it is PFR or MFR or a recycle reactor. But here one important thing is how we draw this. How can we draw these rates? That's the big thing. And how we draw this reaction path. Either it should be a straight line or a curve or whatever it is. That is what the next things is about. How we draw this reaction path by using this adiabatic lines and all. Especially at what slope you need to cut this particular thing. This depends on, I'll just show you. It will depend on one T. Yeah, you can see here XA. Yeah. Yeah, XA versus T. XA versus T. This is the curve. So from this, rest of the thing is all same. So this you will write as like this. XA is T. So XA is 1 plus beta T. I think I'm not sure whether I'm writing here. XA versus T. Yeah, this is how. XA is T into K naught. By using this particular equations, we can calculate the slope, right? That we'll see a bit later when we go to that adiabatic processes, right? So here important thing is, the important thing here is I'm going back again. Here, drawing this curves and drawing the reaction path and seeing where it is being touched. And seeing where it is being touched. Accordingly, the corresponding XAs and corresponding RAs you'll note and then draw 1 by RA versus XA. Then you can give the area under the curve is PFR. MFR is just a point. So draw a rectangle around that particular point. You know what is the conversion required. Wherever it is touching, then draw it. And this will be for the recycle process. Right? So how to draw this particular lines? I show you in one problem. Just go through the problem. You are having still time, especially a lot of time you are having for the next class. Please go, read this problem. Problem is 6.1 in this Gavane. Yeah, Gavane 6.1. This is 1. I'll just show you that. Please go through this first 3 problems. This problem he is talking yesterday. I am talking about that formulas, right? Delta HR, how to calculate, right? Yeah, this is the curve. How to draw the curve? This 0.3. Please see this. Determine the equilibrium conversion for the following elementary reaction at 0 and 100. A is giving you R like this. He is giving you delta G, delta HR, Cp is giving. He is asking you to construct a plot of temperature and conversion. What restrictions you will be putting. So he gave delta G, delta HR, right? I'll just go through this. This is the reaction given. Delta G is negative. Delta HR is also negative. That means that it is an exothermic process. He gave CPA, CP are constant. Therefore, delta Cp will be 0 because both are same. Delta HR is nothing but it's 25 degrees centigrade standard. That is what he is giving you. We know that delta G is minus RT ln K. So we need to find out K. K is nothing but delta G by RT. Ln, if you take this side, it becomes e power minus. So substitute that and then calculate. K at 298 degrees centigrade is 300. But we don't know K at higher temperature because the temperature is ranging from 0 to 100. At 100, we don't know what is K. That we will do by this reaction. We know that ln K2 by K1 is minus delta HR by 1 by T2 minus T1. T we need to T1 is 298. T2 is T is 100. So any temperature you have to take. So we need to get an equation in terms of T. So ln K2 K by K 298. 298 is that K. Delta HR by R 1 by T minus 1 by T8. If you substitute delta HR and all, we are getting one equation K is 300. K at 298 is 300. That is what we calculated. Exponential 75300 by RT minus 30.4. So this expression you are having in terms of T. You go on changing the T, you get different case. That is what we do. Now this is a irreversible process. Minus RR, rate of disappearance of R is K1CA minus K2CR. So we know that CR is CA0 into XA because initially there is no R. So CR is CR0 plus CA0 into XA. So if you substitute in this particular equation, then you can get K. So XAE is K by K plus 1. That is the equilibrium constant by K plus 1. That is what for a irreversible process we already derived. So K is XA is KT at a temperature by KT, is a function of temperature plus 1. So K is a function of temperature. So from this you can calculate XAE. We already have K, one formula. That K you substitute here, calculate XAE. So put T is 0, 100, 20 and 100 because you are having the limit from 0 to 100. That is what he is asking. So put some values and here and then try to calculate. K is this particular thing. Put the temperature. Substitute the temperature, you get a K. K you substitute here and then calculate XAEs. That is what. So at T, convert to Kelvin, you can calculate K by using this particular formula. Then once you calculate K, XAE you can put, because XA is 1 K by K plus 1. So you get that. Then draw XAE versus T. Then it goes down. This itself indicates that it is exothermic process, because exothermic process, as the time increases, temperature increases, your equilibrium conversion will come down. Right? So please go through this problem. This is how you have to draw XAE versus T curves. That is what I am just showing you here. That is what I am showing you here. XA versus T at different rates. The different rates will come from this particular thing. This is for one particular rate, right? This for this particular rate. So one more rate, again one more curve will come, which may be coming like this, right? Yeah, this problem you try to do, and you try to do some more problems, just like some 5 problems which are important. First 5 problems. I'm not having much time for you to talk about all these problems. Please do it. Then if any difficulties is there, you can always we can have a discussion. Right? So with that, I'll stop. I know if you understand, it is fine. Otherwise, we'll see in the next class. Right? So go, Guru. 58 or 57 are there.
Yes,
Minus
sir.
1, it is 56. So around 9 absentees may be there. Take the attendance. And if any doubt, you please let me know. Yeah. Open for your
Yes.
discussion now. Yeah. Open. Any doubt you want to ask on this?
Sir,
Yes.
that question, how did they find from the graph the XAE possible 75 they have given?
Where is it? Here.
That Gavane question have you solved, sir?
No, yeah. XAE. Yeah.
They have given the temperature allowed is 78%. From the graph, it is clear that the temperature above the graph they have given the final line. Yes, sir.
Yeah. No, XA is 75. For a 75% conversion, your temperature is around 78. If you operate your reactor at a 78, then you can get XAE is 7. That is because that second question I asked, right? You put a thing. What restriction should be placed on the reactor operating isothermally if the conversion is 75%?
Yes, sir. I didn't
If you
see
want
that.
75% conversion, that is why he's putting a conversion that if you are having a 75% conversion, your reaction should not go more than 78. If you are having more than 78, definitely your conversion will be less. If you are having your reactor less than 78, your always conversion will be more than 75. Right? So you try to operate your reactor less. At this particular point, you get XAE as 75. That's the question he asked. Okay. Yeah. Any other? Okay, if no questions, I'll wind off and we'll meet on Thursday, I think. That is a regular period. Tuesday, I think I am not having period now, new timetable. Thursday, we'll meet second hour. Okay. Thank you for joining. I think Guru might have taken the attendance.
Thank you, sir.
Yes, sir.
Okay. Thank you. I stop the sharing now. And